am Dr. Frank Summers of the Office of Public Outreach. When you came in, you got a brand new lithograph. I hope you got a brand new lithograph of supernova 1987A. And this is in particular discussing what supernova 1987A looks like 30 years after the explosion. There's a lot of things that don't change in astronomy over the course of a lifetime. Supernovae, they're one of the things that actually do change over the course of your lifetime. Flip over on the back and you can read some of the changes that we have learned, and so we still have more cool stuff that we're going to learn from watching supernova 1987 develop. It's just changed from one phase into the other phase in around 2016, so it's a cool time to be watching it, and we'll continue to watch it as long as we have telescopes to look at it. All right, tonight's talk will be active luminous blue variables in the large Magellanic clouds. It's a mouthful, but Nolan will explain it in great detail for you tonight. Next month, we have a really, really cool talk, Cassini's grand finale at Saturn, and I'll tell you just a little bit more about that during the news summary. Bonnie is our Saturn and Saturn ring expert here in the building. So I twisted her arm. Actually, I gave her no choice. I said, look, you've just got to do this. And she was like, yeah, I guess I got to do it. Okay, so we'll do that. And then November and December haven't been scheduled because astronomers don't respond to their emails over the summer break. I'm waiting. Seriously, I waited until after Labor Day, and now I'm sending out the email tomorrow, and I'll have those and the rest of the schedule filled out relatively soon. If you want to find out about what that schedule is, you can go to our website, use your favorite search engine and put in Hubble Public Talks, and you'll find the upcoming lectures listed here. You can also watch live. Here are the links to the live webcasting, the archives of the webcasting back to over 10 years of talks, and you can sign up for the email announcements, which will remind you each month of who's talking. All right, as I said, the announcements, you can sign up at the website. If you do not like going to websites and you want to just hand me a piece of paper with your email, that also works as well. If you have comments or questions, just send them to publiclecture@stsci.edu, and I or one of my colleagues will respond. Social media. We have Facebook, Twitter, YouTube, and Instagram channels that are officially supported and have regular posts on them. We have my stuff, which is my blog, my Facebook, Google, and Twitter, which are not regularly updated. In particular, the last month I've been traveling a lot. I don't think I've put anything up in the last 3 weeks. But I will make up for it this month probably as I start to get my eclipse stuff put out there. Guess what? There's no observing tonight. Those of you carrying umbrellas in understand this. But they have, Maryland Space Grant Consortium has just redone their website, and they have observatory status right on their page for the Morris W. Offutt Telescope. So if you go to their page, md.spacegrant.org, click on observing, you'll get this page, and it will tell you what the status is for this Friday, September, what does that say, 8th? Yes. And it says check back Friday at 5 p.m. to find out if the observatory will be open, okay? So the staff will update this at 5 p.m. You can come in and you can actually do a longer observing session on the Friday nights than you get to do after this, especially tonight since you won't be able to do it today. Okay. All right, now let's do our news from the universe for September 2017. Anybody want to guess what the first story is? It is, of course, the eclipse-o-rama. So the question I most got was, did you go on vacation to see the eclipse? And my answer was, of course, no. I did not go on vacation to see the eclipse. I went on vacation to see Yellowstone National Park and answer the ultimate question of, where does a 2,000-pound bison walk? Answer is, of course, everybody together, anywhere he wants. This guy here decided he was going to walk across the street and right through the parking lot. I mean, in between cars in the parking lot. he wasn't more than 20 feet away. We saw some moose. There's a mother moose and her calf eating lunch in a pond. This is the Grand Canyon of the Yellowstone, the lower falls, and we saw geysers, and more geysers. We had a really great weekend. Actually, we left the geysers to last, and we just got like 10 geysers in great eruptions in 2 days. And then, of course, my favorite, which we saved really till the last, was Grand Prismatic Spring. How many of you have seen this? I mean, it's just so technicolor. You really almost, even now you go, was that real? Yeah, it really was real. Those colors really are real. And so we had a fantastic vacation in Yellowstone because eclipses could be clouded out. So on the way home, after we finished our vacation in Yellowstone, we dropped down into Idaho, and it was totality or bust, as we saw in this one car in Idaho. We went to Rexburg, Idaho, and they threw a festival. They had 100 tents and vendors and food trucks. They gave over their whole public park to camping. They probably had 50 to 100 people camping out for the weekend. And the movie theaters were very, very on the ball. They put up signs like this. The 3D glasses at this theater are not safe for viewing the solar eclipse. The mini mart had an eclipse sale for the 3 days around the eclipse. I mean, it was just fun to have people get involved in it. And so I, being my first total solar eclipse I'd ever seen, just sat back, relaxed, and did not use my 3D glasses. I used my actual solar viewing glasses and sat back and enjoyed it. I didn't take any photographs, but my son used his iPhone and he got something like that, okay? So I was impressed. Like I didn't even try, and he was able to get that with his iPhone. Fortunately, and I knew there were plenty others who got some really great pictures, including our master image processor here at Hubble, Zolt Levay. He was in Jackson Hole. There was an art exhibit of some of his photographs there, and he got pictures like that. Isn't that cool? So that is the corona and all the details and the striations of the solar wind blowing out away from the sun. Zolt is an accomplished one. And this right here, he says, is the star Regulus. Okay? Yes?
Could you see all the striations move? I've
Yeah.
never seen an eclipse in totality.
Okay. So you could see about, I'd say 60 to 70% of the detail he shows here with the naked eye, which was really cool. Okay, because I, as a professional astronomer, had seen pictures like this, and I'd never seen a totality before, and the amount of detail in the striations I could see surprised me. They didn't move. They were pretty much stationary. Yes. That's Regulus. That's Regulus. I could see about 10 stars around the sky. It was just really cool. And you know, this was a festival in Rexburg. There were like 500 people, and they all started cheering and clapping and applauding when it hit totality. Most of them probably didn't know what to expect. And it was just really cool to have the whole swell of everyone going, whoa! And you know, people were just spinning around going, oh wow, this is crazy. For 2 minutes. So 2 minutes of craziness in Rexburg. Zolt also got pictures of something called Bailey's beads and the prominences. So actually, this is a really cool pic. You can see the prominence on the edge of the sun, and down here you can start to see a little bit of beading along up in here. I couldn't see any red or any detail like that. I could see individual little dots just as you came in and out of it, but it was very quick. And then, of course, you get the big diamond ring effect. All right, Zolt put together a montage from first into a little bit of a beating to totality, and then pulling out. And this was what I remember most, was that as it goes into totality, you have your glasses on, and you don't take them off until it hits totality. And then you see the corona. But as it comes out, you're going, I want to watch this as long as possible. And then it starts to bead, and then boom, you get that diamond ring, and you go, okay, glasses back on. And that was a lot of fun. So that's really cool. I think we got a lot of people in America to understand that a total solar eclipse is really interesting, which means that the traffic, which was horrible getting back to Salt Lake City this time, will be even worse next time, which is only 7 years away, April 8th, 2024. We get a 4-minute total solar eclipse passing. The peak is somewhere down here in Mexico. It goes through, passes Austin and San Antonio, goes straight over Dallas, goes all the way up through the northeast and goes out over Canada.
Do you remember what community is at the intersection of the...
Carbondale, Illinois.
Carbondale.
C-A-R-B-O-N. Yeah, Carbondale, Illinois gets totality for both of these eclipses, okay? It's the eclipse capital of the U.S. for the current set, all right? Anyway, so I hope, how many of you actually got out to see totality? All right, good. And did the rest of you see partiality at least? Okay, good. I expected my audiences here would have at least seen partiality. But if you haven't seen totality, it really was more than I expected. Even though I knew what to expect, it was a lot more. So try and get it. It's a really good bucket list item. And you got a relatively easy one. You can go to Cleveland, okay? Have a great vacation in Cleveland. If I make a bad joke about Cleveland, I have a friend at Case Western who will punish me for it. So I'm not going to make any jokes about Cleveland, okay? All right. So that's my wrap-up of the eclipse. There are some amazing photographs online and videos and such, and I encourage you to check out and see all that other professional stuff. All right. There is another major event happening, and that's this month in September, is the Cassini Climax. Cassini was launched 20 years ago, almost 20 years ago, October 1997 it was launched, and it will be crashing into Saturn on September 15th, 2017, and they estimate signal loss will occur about 7:54 a.m. Eastern Daylight Time.
Somebody?
Well, the point is that they want to make sure that they don't contaminate anything, okay? All right? You know, if they let it float, there's a tiny chance it might hit Enceladus, and if there's any prebiotic life on Enceladus, we don't want to contaminate it or anything. So, like we did with other ones, we're going to smash it, we're going to crash it into the planet, and we're going to learn about the details of the atmosphere of the planet as it goes in, because for the last 3 or 4 hours as it goes in, it will be doing a real-time data stream. And I looked it up, that real-time data stream will be 27 kilobits per second. Wow. That is the speed of a 28.8 modem that was first sold in 1994. Yeah. So Cassini will literally be on the internet phoning home with its final data. All right, I'm not going to say anything more about Cassini because Bonnie Meinke will give you the full scoop of this next month, but this will be a fun event, and NASA's publicizing it. You'll see all sorts of cool stuff about it over the month. See a little bit, and Bonnie will explain to you what it all means next month. All right, finally, I have to give you at least one science story here tonight, and it's called Into the Stratosphere Exoplanet Edition. Now, Earth's atmosphere is segmented, okay? We live and do almost everything down here in the bottom layer of the atmosphere called the troposphere. And in the troposphere, this is a graph of temperature versus altitude. Temperature goes down in the troposphere, okay? As you go higher, it gets colder, right? But at a certain point, it actually turns over and starts to get warmer, and that is the layer of the atmosphere called the stratosphere. The point is we're trapping, the greenhouse gases are trapping heat down here in the troposphere, but it's being heated by UV light in the stratosphere, okay? And then it turns over again into the mesosphere, it turns over again into the thermosphere, and really you're up at what we consider the top of the atmosphere, and everything else out here is the exosphere, which is, of course, where Hubble and the Space Shuttle and the International Space Station are, okay? So the point is that we understand Earth's atmosphere, and it's got these temperature inversions. What we would want to know is, are such temperature inversions characteristic of planets around other stars? We see this temperature inversion here. What happens on other stars? Well, Hubble has a spectrum of a planet called WASP 121b, okay? And in looking at that, they're trying to determine, does it have a stratosphere? Are the outer layers warmer than the inner layers? If the outer layers are cooler, then they will actually absorb light from the lower layers, whereas if the outer layers are warmer, then they will emit light, okay? So you've got two graphs here. This is purple. This is the spectrum for a brown dwarf. That shows it in absorption, okay? So the outer layers of the brown dwarf are cooler. They absorb in the water bands here in the infrared, whereas Hubble's spectrum actually shows emission at those same band passes in the infrared. This is what they tell me, the strongest evidence so far that they have seen a stratosphere on a planet around another star. And this is the kind of cool thing we can look forward to over the next couple of decades. We can check to whether or not the things that happen in our solar system also happen in other solar systems. Is our solar system somehow special? We hope not, because we based a lot of our scientific projections about the universe on our solar system. But this is the kind of thing that shows us that, okay, yeah, stratospheres also exist on extrasolar planets. That's kind of cool, isn't it? So, of course, a squiggly line is for the spectrum is not suitable for a press release. So, of course, they had to come up with a cool artist illustration. And so this is the star WASP 121, and this is the planet WASP 21b. Because it's so hot, its outer atmosphere is at around 4,000 degrees, they say. They believe that some of the molecules are actually being evaporated from the planet and might be blown off in a wind. But it's very hot on its near side, it's tidally locked, and it's actually slightly egg-shaped because it is filling out about, what they said, about 60% of its Roche lobe. All right, and the Roche lobe is the radius at which it actually becomes totally distended and material can flow away freely, okay, by gravitational. So this is the pretty artist conception that they had our artists make to show it off. All right.
Quick point.
Yes.
Question. Define a brown dwarf, please.
Brown dwarf, thank you. I did use jargon, I forgot to mention it. A brown dwarf is an object that's between a planet and a star, okay? A star is powered by, a main sequence star is powered by hydrogen fusion in its core. A brown dwarf reaches deuterium fusion, but never gets big, it's not big enough to reach hydrogen fusion, okay? A planet like Jupiter never reaches deuterium fusion, doesn't reach any fusion whatsoever. So the ones that make this tiny bit of fusion and then fade away, those are brown dwarfs. So they're like 70 Jupiter masses and above. Okay? All right, good question. Thanks you for catching me on that. All right, and now we go to our featured speaker. And our speaker tonight is a senior scientist here. And I guessed that he'd been here about 30 years, and he said, no, he'd been here 34 years. And then he said, you know what? I was actually here 5 years before that, helping write the proposal that created this institute, okay? This is a guy who's got so much history. He was here at the genesis of the ideas that created this building, okay? And I gotta say, you know, this institute was a totally new thing in astronomy at the time, because most of the observatories were supported by staff in an astronomy department at some university. This was an association of universities running a specific institute to just do professional support of the telescope, and it's turned out fantastically. Their vision has been executed incredibly well over the last 30 years. Let's see, his official status is as senior astronomer and major primary support for the Space Telescope Imaging Spectrograph. All right, so user support for that. Okay, so ladies and gentlemen, let's have a warm welcome for Dr. Nolan Walborn.
That's on. Thank you. Well, Frank's various introductions here actually caused me to add a few preliminary additional introductory remarks that I wasn't going to. First about AURA, Association of Universities for Research in Astronomy. Actually, it isn't true that this institute was the first place that operated this way. AURA founded Kitt Peak in Arizona and Cerro Tololo in Chile in the 1950s and the 1960s, and these were the first visitor centers where anyone could come and observe based on competitive peer-reviewed proposals instead of just people who owned the telescopes. So AURA already had that paradigm in mind when we proposed to NASA to manage this institute, and were successful against many predictions, since Princeton had in some ways first dibs on it, but I guess our proposal was better. And I was on the Cerro Tololo staff in Chile when I came here and did that in 1979, which also relates to the litho that was distributed, and also relates to my talk. So I thought I'd say a couple of words about that. This is, probably most of you know, is the first supernova this close to the sun since the invention of the telescope. So that was 1610, by the way, so we're pretty excited about that. And I'm going to be showing you some very peculiar, interesting, massive stars which are near the ends of their lifetimes and behaving very strangely. We don't understand the details of why they're doing this. That's what we're working on. But as you know, probably all massive stars end their lives as supernovae, final collapse and explosion, or maybe implosion in some very massive cases. Yeah, we would expect them to do some strange things before that happens. Not this one. This star is only 20 solar masses, although that's twice as massive as the lowest masses that make supernovae. And the star was known as just a normal, ordinary blue supergiant, and the LMC, no one paid much attention to it until one fine day, February 23rd, 1987, it blew up. And then it was too late to go back and study the details of the star that blew up. We very much wish we had done that, but it did nothing exceptional to draw attention to itself until it exploded, and that was a big surprise. These stars will explode sometime soon, and they are drawing attention to themselves. So this lead image here is the whole Large Magellanic Cloud, which you may know is a relatively small, well, moderate size satellite galaxy of our own that is very important to the study of many things, because it is far enough away that we can see it as an independent galaxy. It has its own evolution and heavy element content, different from our galaxy. But yet it's near enough that with large ground-based telescopes and the Hubble Space Telescope, we can study individual stars in it. And so that's a very useful bootstrap between what we can do in our galaxy and then more distant galaxies where we don't have this level of resolution and information content. So as I've already mentioned, we've been working on these very peculiar variable stars, and I just published a paper, we just published a paper with my collaborators there, all of whom happen to be from Argentina. I wasn't born there, but I spent 8 years there when I was a child, and the other 3 are Argentines, although 2 of them now work in Chile, Las Campanas and La Serena, close to the big observatories like Cerro Tololo and other ones, because the climate in Chile is better than in Argentina for astronomy, and so it's a hotbed of major international observatories, some still under construction. So this shows you the location of the 3 objects I'm going to be talking about tonight. The paper actually involves 5, but these are the 3 that we have the most information about in our study. And I'll start by showing a graph and a few images. But this talk, I'm going to show you mostly light curves, that is how the brightness of these stars change as a function of time, and spectra. Oh no, not spectra. But I hope to convince at least some of you by the end of this talk that spectra are at least as beautiful, if not more beautiful, than images, because they tell you so much more. That's how we learn the physics of the stars. is from their spectra. And so I'm going to, not going to assume, some of you maybe have some familiarity with spectroscopy, and but I'm going to explain some for those who don't and may be interested in that, because you can learn a lot if you bear with me and follow some of the details that I'll show you. But we're starting off here with a graph, the only graph I think I have. It looks pretty complicated, but don't worry about it. We're not going to talk about everything that's in here. You can begin by ignoring all the red and blue points. Throw them out. Those are for something else. We're interested in this green triangles and lines there. But first, I'm explaining what the diagram is. This is a Hertzsprung-Russell diagram, in particular a theoretical Hertzsprung-Russell diagram named after two of the most outstanding astronomers of the 20th century who discovered it. And they worked with observations first, namely the brightnesses of the stars and their spectral types. This has now been converted to temperatures. These are tens of thousands of degrees Kelvin from, oops, now I did it. From 50,000 degrees, the hottest stars, to 10,000 degrees. So these are all hot stars. The sun is 6,000 degrees, so it's kind of even off this graph. So these are massive hot stars. Massive stars get hotter, and surprisingly enough, they have shorter lifetimes than low-mass stars like the sun, because despite the fact that they have more mass, the nuclear reactions are very sensitive to temperature. They have higher temperatures, and they burn up faster, even though they have more material to burn. So this bold line here at the left is the main sequence, which is a very important discovery that Hertzsprung and Russell did. And if you plot up all the stars in the sky that you can with their parameters, 90% of them lie along that line. And I didn't think I did it that time. Why is that? We now understand why that is. When people discovered this, they didn't. But we've made a lot of progress in the last decades. So that is the locus of stars in this diagram of luminosity, increasing upwards, and temperature, increasing leftwards, while they are burning hydrogen into helium. And that is 90% of the lifetime of any star. And so they lie on this locus, and that's called the main sequence. And here it's labeled in masses. You see from 15 times the mass of the sun up to 60 times the mass of the sun. And some of the stars we're talking about are more massive than that. Then you see these lines drawn on here. These are evolutionary tracks. So that's what the stars do in this diagram when they start to run out of hydrogen fuel, and they begin to evolve, as we say. They follow these tracks in the HR diagram, and we now understand a lot of why that is, why they do that. And they take a certain length of time to evolve, as we say. And these dashed lines here are called isochrones. And you see they're labeled in millions of years. And so that tells you how far the star has moved away from the main sequence in that length of time. And as I said, the more massive stars go faster. And you see that in 2 or 3 million years, these stars up here at the top are all the way over here. But here in lower masses, 8 or 10 million years, they're just probably still burning some hydrogen to helium, because this glitch here in the tracks is where they really run out of hydrogen. So we're interested in these green triangles, which some of which are single, but some of which there are two of, joined by a dashed green line. And that is how these luminous blue variables behave in the HR diagram as they're undergoing outbursts. And so these stars are so luminous that they can't hold themselves together. A star is a battle between gravity trying to collapse it. Its fate is sealed as soon as a star forms. A star forms from a cloud of gas in interstellar space that begins to contract and heat up, and it gets hotter and hotter until it reaches millions of degrees in its interior, and that's where nuclear reactions begin. And so that produces a pressure outwards. And so a star is just a huge mass of gas in equilibrium between the gravity inwards and the pressure from the nuclear reactions outwards. And as long as you can maintain that, you have a stable star. But as I already mentioned, it'll run out of fuel. It's burning fuel, and the most of its lifetime is spent burning hydrogen, the simplest atom, into helium, the next atom, the periodic table. But then it can go through subsequent stages where it gets even hotter and burns heavier elements into even heavier ones. And in fact, that's very important because those nuclear reactions not only allow stars to exist, but they synthesize all the chemical elements in the universe, heavier than hydrogen and helium, which come from the Big Bang, a little bit of lithium maybe. But everything we're made out of was made inside of stars. So the atoms in your body were made inside of a star or in the explosions. The heavier elements are really heavy elements, heavier than iron. Many of them are made in the actual supernova explosions when these stars die. And then that's blown out into space, and new generations of stars can form out of that enriched material. And the sun is at least a second or maybe a third generation star, because we could not exist with the chemical composition of the first stars. It's hydrogen and helium. You can't make molecules and people out of that. So you need these heavier elements made in successive generations of stars in order to have life and everything else we have here on the Earth. Well, getting back to our main story here now, these massive stars, they get into trouble when they try to move over here. And they get more luminous, and their winds, the stars, even normal massive stars lose material all the time through stellar winds, but it's a steady, quiescent flow, and that's okay. But here then they start to get unstable, and they can't hold themselves together. So these stars have developed kind of a last-ditch mechanism to extend their lifetimes, if you will, which we still don't understand in detail, in which they have these episodes of enhanced mass loss, and they inflate, and they become cooler. You see them becoming cooler, but this is not the evolution, the nuclear evolution of these tracks. This is an event which takes place on timescales of thousands of years or hundreds, thousands of years, and can repeat. So the star gets here, undergoes this instability, moves over here, and it moves back. And it can do that several times with enhanced ejection of material. That's what a luminous blue variable is. It's an unstable, massive star near the end of its lifetime. This dark line here is called the Humphreys-Davidson limit, after two astronomers who discovered it and found that there are no stars over here. You go over and there are red stars over here, but there's a limit that goes kind of like this and that. And you look at the most luminous stars in external galaxies, and there are no stars there. They don't make it there. They hit this instability limit, and they do this. And then we thought then they lost a lot of material, and they became another kind of peculiar star called the Wolf-Rayet star before exploding. But now, just within the last few years, we have evidence that some of these stars explode directly as luminous blue variables. So that's our hope, that we'll see one do it. You know, our real block right now in understanding the end stages of massive stars is seeing a star that we know and studied well do it. First thing we see is a supernova explosion, some distant galaxy, and it's too late. You can't go back and see what kind of star did that. You can try to get some information, some inference, and maybe you have some old images where it was there. But we would like to see one of these stars that we have observed doing all sorts of things explode, and then we would know things that we don't know. So actually, two of the three stars I'm going to show you are in this diagram. R127, it's Radcliffe for South Africa, where they describe some of the stars. They're in the Magellanic Cloud, the large Magellanic Cloud. R127, it's been observed to have this huge excursion here from 30,000 degrees down to 10,000 degrees and back again. And R71, and you don't want to believe the plot. That's this little line here. You don't want to believe that too much because it looks like it had lower luminosity, lower mass, but and it's now an outburst. As we'll see, it's the brightest star in the large Magellanic Cloud right now, and I'll show you that. And it's moved up as opposed to horizontally as these stars do. And so, there's always new stuff to discover and then try to understand in astronomy. So now, some of this is kind of technical and difficult, and I'm really trying to do my best to explain without jargon, but if I don't succeed, I welcome a question or a clarification as I'm talking. Any more extended discussion, let's save that for the end, because otherwise I won't get through it. But if I use a term or something, or said something that isn't clear and you think can be clarified with a few words, please do. Like, here's one.
So you said that it's varying on the order of the thousands of years.
Mm-hmm.
But then how do we know that they're varying like that? Obviously, they can
Some of them we observed varying. We haven't obviously observed many for thousands of years yet, but they have both outbursts and eruptions. And I'm going to be talking about outbursts mainly, which are these things that last decades maybe, and we have observed the full cycle. For one we had, and I'm going to show you for the first time. Most people didn't see it till last month when a paper came out, the second one, which is observed over the full range of outbursts. But then they more infrequently have giant eruptions in which they eject much more denser material and create circumstellar nebulae. And we've observed some of those events probably, but more than that, we can observe such events ejected thousands of years ago, and for how long ago from their velocities and sizes, how long ago they were ejected. And that's where that thousands of years comment comes from. So that's a good question.
What is the cause of the retrograde that I see on each one of those?
Why does it go back?
It goes up to 10, it goes back, and then it goes across. Every one of them is a little retrograde in each one of them.
Oh, this little glitch here?
Yes.
That's the terminal age main sequence, and that's where really the hydrogen burning stops completely. And so, this is a plot of brightness versus temperature. So when stars get to that point, they do a little retrograde, that's a good word for it, a little glitch in this diagram, and that's as their interiors readjust, and then they cross, especially these lower masses, they cross this pretty rapidly, and then they go over here and become red giants, red supergiants, where they then burn helium into carbon, and that can last 10% of the hydrogen burning lifetime, a million years for a star that lasts 10 million years. And so this is part of the readjustment of the star's interior as it goes from losing its hydrogen source to gaining its helium source. But and then it can go on and burn carbon and burn other various elements up to silicon, the most massive stars, and that lasts 3 days. So they run out of tricks, and then there's the final collapse because the energy goes away, but the gravity is always there. Good questions. Was there another one? Okay, well, let's move on. I'm not going to spend this much time on all of the diagrams, I hope. So first object we're going to observe is R127, which you heard about and saw. It's located near 30 Doradus. Those of you who've been here a lot before and heard some of my previous talks are familiar with 30 Doradus. This is the 30 Doradus region. Actually, the 30 Doradus nebula is half off the screen here. It's up here because that's not what we're talking about today. This is the site of formation of the most massive stars known at the present time, up to 300 solar masses. We didn't know until very recently that there can be stars that massive. But you see all these different kinds of structures here, some with nebulosity, some without. These are all massive stars. They have different masses and ages, evolving, doing their thing in this large region. And if we understood why every star is where it is, and these nebulosities, some of which are ejected and some of which are just fluorescing, we would know a lot more than we do today, and someday we will. This is what we study. And in particular, we study R127, which I haven't marked, but I can point out to you in this. Supernova 1987A, by the way, is right there. Oh, and I forgot another thing I was going to mention. You see in your diagram here, the supernova 87A is inside that ring, the famous ring. Then there are two stars beside it. Those are called stars 2 and 3. And the original star that exploded is star 1. And it was originally 3 magnitudes brighter than those other 2 stars. It was 12th magnitude, and those 2 are 15th. That's a factor of 16 in brightness, so you can believe it's not there anymore, right? What we see there in the middle is just the blast wave from the explosion coming out, but that star is gone. So we know that. But there was initially some confusion about which star had exploded and how many stars there were there, and I actually discovered star 3. The fainter one down here, just as a bulge on the overexposed image of the star that exploded. In pre-explosion images I had of 30 Doradus from back when I was on the Cerro staff. And I got some credit for, there was a telegram came out saying, that the star hadn't exploded because there were still 2 stars there. Yes, there's still 2 stars there, but not that one. So here, this is a fantastic region. It contains 87A, which is, as I said, right there in that little group. And here See this little group of stars here? I want you to see 2 bright stars and then 2 fainter ones up at an angle there, okay? And the one here, the bright star, the brighter star to the right is R127. And that's a star I'll be showing you some bizarre current behavior of. But that's where it lies. You see, it's in an evolved region, okay? The youngest regions have all gas and dust. Here, these stars have evolved and they've blown it all away. It looks like, almost like a ring of stars here. And you can just tell by looking that these are older stars than the ones in 30 Doradus because they've blown away all the gas and dust that they had around them after they formed. But this is a low resolution, large field thing, image, which is useful to have, but we want to know more. We want higher resolution and more detail. And so here are those same stars I just showed you in a higher resolution image. Now what looked like the 2 brighter stars are actually these 2 clusters. They weren't single stars, and that's a big problem, even at the large cloud, which is the nearest neighbor. Is this really a single star, or is this 2 or more stars so close together that we can't resolve them? And so we're always looking for higher resolution to answer that question. So you can see, so these are kind of quiescent blue stars in these clusters, some brighter ones, some fainter ones. But here is R127 itself, surrounded by this red halo. And I didn't put that there, it's there, drawing attention to itself. And actually, when it had its major outburst, which I also helped discover in 1980, it became much brighter than this star. I went down to Saratoga to observe after I left the staff, and I went to the field, and I sat there for a while until I figured out what was going on, because the field was completely different from what it had been the last time I looked at it, and it's because this star, which had been the brightest, was no longer the brightest, and this one was way brighter by several magnitudes. What this red glow is, this is an example of one of these circumstellar shells that was ejected a few thousand years ago, maybe. And it is glowing in the light of nebular emission lines of hydrogen alpha, but also especially nitrogen, which are 2 strong lines on either side of H alpha. And these stars, these massive stars, they undergo nuclear reactions. I can't give you all detail of massive stellar evolution in the time I have, but massive stars burn helium to hydrogen on what's called the CNO cycle. It's a series of reactions which very rapidly lock up all of the carbon, nitrogen, oxygen in nitrogen, because that's the slowest reaction. It's a bottleneck. Now, if this material gets mixed up to the surface of the star or ejected before the reaction goes to completion, you can see that. And so you can actually see the nuclear reaction products of a given star on its own surface. Isn't that amazing? And that tells you, of course, an enormous amount about what the star is doing, how it's evolving. And yes?
How far away from the other stars in the cluster is R127? Maybe just the other star right next to it. I know we can't really see the depth there, but
yeah, a few parsecs. I happen to know that the now this is actually I said it's high resolution image, and it is higher than the previous one, but it's kind of low actually. There's structure in one can see in even higher resolutions within this nebulosity. I was just reading about it, and so the size of this nebula around the star is about 2 parsecs, which is 6 light years. So that gives you an idea of the scale. So these stars are a few light years away from each other, but still within a compact cluster. And this nebula that R127 ejected has expanded to engulf that star, or maybe it looks pretty blue to me. Maybe it's in front of the nebula. You can tell this isn't a great image too, because the star images are all kind of fuzzy. We don't like that. That's bad seeing introduced by the Earth's atmosphere. So this is an excellent observatory in Chile where they have very good seeing some nights, but not on this particular one. Yes?
This question was pretty interesting because does it mean that they are twin stars? They are close enough to be bound to each other?
Sure. Yes. That's a huge subject, the binary stars. And in fact, most stars, especially massive stars, are binaries or higher multiples. And so instead of a single star like we have in the sun with planets going around it, you have 2 stars going around each other or around their center of mass. And massive stars like to be binaries, and this tremendously complicates in the study of their evolution, because when they start to evolve and expand, then they interact, and one star might dump material on the other one, and all kinds of bad things can happen, or good things, depending on how you look at it, but it makes the study of stellar evolution a lot harder. Okay, well, let's go on here now and see. So I'm not going to show you any more images. Now we're going to see what these stars, these three luminous blue variables, are doing right now. So first, this is our first light curve for R127. See the star names are up at the top there. And so the year is up at the top, the bottom is Julian days, and you can't remember what those mean, but they're useful. But you can see then that this sequence of measures, individual measures of the brightness on different dates, goes from just before 2008 to just this year. Or we have 2017 for some stars. I don't know if we have for this one. So this is amazing, and it was a little bit embarrassing because we wrote a paper in 2008 about the giant outburst of R127, which, as I said, was discovered in 1980. We studied it, for almost 30 years, and then it came down. These are points from our previous paper, published in 2008. And so the title of the paper was "The End of a 3-Decade Outburst of R127." Before the paper even appeared in press, went back up again. And that's what they do. We don't understand them. We don't understand why they do this. And now, as opposed to this sort of 30-year outburst with fluctuations in it and everything, which I'm not showing you because I can't show you everything I have, now it's had like 4 these undulations with time scales of 2 or 3 years. Why is it doing that? What does it mean? Is this reverberation or a reaction to what happened before, or is this going to become a supernova and give us the delight that we would hope? It's falling apart completely and will explode. So that's what it's doing, and unfortunately I can't explain to you why or how, but there are obviously some instabilities inside the star related to the ending of the nuclear reactions and these LBV excursions, and that's what it's doing. Now these marks down below are epochs at which we have spectra, both high resolution and low resolution spectra, and that's what I'll show you next and try to explain a little. So the upper ones are high resolution spectra and the bottom are low resolution. So first I have here a montage of, these are V magnitudes here. So a magnitude, as you may know, is a factor of 2.5. 5 magnitudes is a factor of 100 in brightness. So this thing ranged over 2 magnitudes during this period, although it was brighter than that. It was 9th magnitude up at the top of the 1990 maximum. Well, here is a sequence of spectra, which Frank has kindly made brighter, so we can see the labels a little better. And I want to spend a little time explaining them, because I'm sure most of you are not familiar with astronomical spectra, maybe not any spectra, and we have a certain notation. So the first thing you see is all these lines, right? Most of them going upwards. Those are called emission lines. Actually, that was useful. We had an introduction here about a planet in which cooler material produces absorption and hotter material produces emission. Same thing is going on here. And so there are a few absorptions you can see. We'll see in some more spectra later, which are dominated by absorption. But these are, each one of those lines is a transition of electrons in an atom. Now, most of you probably know that matter is made up of atoms, the chemical elements, and they have nuclei with protons and neutrons. The protons have positive charge, and then in the neutral state they have an equal number of electrons to protons with negative charges surrounding the nucleus. So they're electrically neutral. The electrons are negative and the protons are positive. But a very interesting, important thing is if you increase the temperature or decrease the pressure of the gas containing this material, these atoms can be ionized and lose an electron or 2 electrons or more, depending on how many they have. Of course, hydrogen only has 1 to lose, but helium has 2. And when that happens, then we call that an ion, not an atom anymore. And furthermore, its spectrum is completely different. All the lines which it produced as an atom are gone, and a whole new set of lines is produced by this ion, because the electronic states are changed by the fact that there's one fewer electron there. And so if you get transitions, these electrons can be different states. They have their sort of lowest states, but then they can get excited up to higher ones. And if an atom or an ion absorbs a photon, an electron can move up to a higher state. But then it can move down and emit a photon. And so electrons moving down create emission lines, and absorbing photons produce absorption. So we have a continuum here for each spectrum. These, I should say, are the spectra of the same star, believe it or not, taken at those dates, which you can read from the back, go from 2008. Did it say 2008 or say 2008 to 2016? And all these huge variations that you see occurred during those 8 years. And so here at the bottom, the star was in a hot state. And so here you see these notations, which are combinations of letters, which are the chemical element. Fe is iron, Si is silicon, He is helium, N is nitrogen, followed by a Roman numeral. And the Roman numeral astronomers use to denote the ionic state. How many electrons has it lost? So if it were neutral, it would be Roman numeral 1. You don't see many ones. Well, you see some helium 1, okay? This is neutral helium. But this is ionized nitrogen. This is doubly ionized iron, doubly ionized silicon. And so these are identifications of these features in the spectrum. In fact, here you see this is mainly an absorption, although it has a little bit of emission on the red edges. Silicon absorption triplet. And then you see this nice multiplet here of nitrogen emission lines. So this tells you right away, by studying the lines, and especially the ratios of lines from successive ions, what the temperature and the pressure of the gas of this atmosphere or envelope producing them is. And you learn the chemical composition, you learn all sorts of details about the physics of the atmosphere or the plasma that these lines are in. And as an added bonus, you get the radial velocity, because the positions of the lines, which are in principle fixed by the structure of the atom, but if there's a motion along the line of sight between the source and you, then they move in wavelength, and you can measure that too. So isn't that amazing? We can get all of that information. And these stars are completely unresolved. They're points. I showed you that the ejected nebula of R127 is resolved, and we can study some spatial structure in that. But all this information about the physical details of the star itself come from the spectrum, because they're so far away that they're just mathematical points. You can't get any structural information from images. So then I think you understand the basics. I hope you do. Any questions or doubts about what I just tried to briefly explain? This is a semester course in 15 minutes, but I think you can capture the main points. And so see how it changes. These nitrogen lines here, which correspond to maybe a temperature of 30,000 degrees, weaker, disappear, gone, no longer there. Now here are all these other lines over here. These are magnesium 2, iron 2 lines, cooler, from a cooler atmosphere. So this star has cooled. It's expanded and it's cooled, and the visual magnitude has gotten brighter. And then now, by the end of the sequence, it's coming back. See here, there are the nitrogen 2 lines again showing up. So over these 8 years, we've observed this star, or this LBV, an outburst, to go from a hotter state through a cooler one, and then back to a hotter one. So that's what we're doing here. I can't tell you why, but first you have to know that it does this, right? If you didn't even know this, you're never going to figure out why. Sometimes we have an argument with theoreticians who don't like all these observational details, but they like to explain things. And it's true, the only way you can explain things is by physics, but you can't explain something you don't know. First you have to discover what happens, and then explain it. usually. Okay, well, onward. Now here, I'm not going to spend a lot of time on these because it's too much and there isn't time, but these are some panels from high-resolution spectrograms. They're much more extended. In fact, they're taken with the shells, which use multiple orders and make a two-dimensional format, because otherwise the thing would be a mile long if it were a single spectrum like those low-resolution ones I showed you. And so the neat thing about these figures, which my colleague Roberto Gammon made, is that what you have along the left edge of each of them is the light curve, plotted vertically, okay? So left is brighter and right is cooler. And then you can look at the spectra and see how it changes as the temperature changes. And so here are these nitrogen lines that I was showing you, and you can see them in a lot more detail. They have what we call a composite P Cygni profile that combines a red-shifted emission and a blue-shifted absorption, and that's a signature of an expanding atmosphere, by the way, or wind. And here they are, you know, when the thing was faint, 2008, now it starts to get brighter, they're gone. And then, as I told you, it's gotten fainter again, and they're back. Helium-1 is even more sensitive. You see, it's strongest when the star is hottest and faintest, and goes away and comes back. It's a very strong helium, neutral helium line here that does that over this sequence. Here you see sodium-1, but those are not in the star. Those are interstellar lines, very narrow, very sharp lines of very low ionization in gas in space between the star and us. It forms interstellar lines. Okay, that's the R127 story that I have. Let's move on to the second object, which is, you know, they have strong similarities, and that's the bottom line of this talk, is the strong similarities between the behaviors of these objects at different epochs and among different objects at comparable epochs. But and then you look in detail, and they all do different things. And look at the dates along the top of this plot. Does that amaze you? So this is another thing we discovered in the course of this work. Harvard University has run these stars, of course, in large magnetic cloud, the southern hemisphere. You can't see them from here. You have to go to South America or South Africa. And they had telescopes down there from the late 19th century monitoring stars and taking spectra. And recently they digitized these data and put them online. And we looked, and lo and behold, R71, which was discovered as an LBV in 1970, you see this gap here, where there's nothing, where Harvard stopped, and no one was doing anything until it was discovered to be an LBV. And had these two huge maxima, right in 1914 and 1939. Maybe you recognize those years. So let's hope that this even bigger one here in 2016, 2017 doesn't follow the same trend. But anyway, this star has been having these massive outbursts during the whole 20th century. We had no clue until we plotted up these Harvard patrol data. And now it's doing this. It had this outburst here, centered around 1970s. And now, right now, as I said earlier on, it's the brightest star in the Large Magellanic Cloud, brighter than 9th magnitude. And let's look at an expansion of that right-hand side there in the next slide. So this just blows up the last few years so you can see what it's doing. And so it was down here and then had this huge rise. And now it's kind of flat, just sitting up there, although you can see looks like kind of a periodic variation there. We're working on that. That may be some kind of pulsation or something that will tell us more about what the star is doing up at this maximum. But it looks like about 440 days, as best you can tell from that information. And so now, that's where it is right now, as far as last check, early 2017. And so we have spectra at the epochs shown below. And this is the most boring slide I'll show you, which is just almost constant absorption line spectrum, very boring. But you see the years there, and look at the previous one, 2010 to 2016, and so this is what its spectrum looks like as it's just sitting up there on that flat, long, broad plateau at its maximum. And these are absorption lines, of a cool atmosphere, iron 2, mostly iron 2 I have identified here, calcium 2, and the hydrogen lines are, even in the sun we still see hydrogen lines, because hydrogen is the most abundant element, and so it forms over a large range of temperatures. So not too much interesting to see there in terms of variations, but of course it's important to know what it's doing and how it relates to the light curve. Here are some high resolution observations of this star, which go back further than our monitoring. We get these from archives, like the European Southern Observatory, back when it was fainter and hotter. And so you can see how the spectrum changes, just like the R127, from hotter species down at the bottom up to these cooler ones that are identified here, but were in the spectra you saw of iron 2. Here's a sort of curious detail, if you're curious about spectroscopic details. Remember I told you these sodium 1 lines are very narrow. That's characteristic of interstellar lines, and they're too low ionization for these hot stellar atmospheres, so that formed there. But now look what happens. They get strong and broad. That's because they're now stellar features. The star has gotten so cool that it can form neutral sodium lines in its own atmosphere. And so the interstellar lines you can see here are obliterated by the star itself. Actually, it's even more interesting that this is a doublet. There are 2 lines. So you see 2 narrow ones and 2 broad ones, okay? The 2 narrow ones are formed in our galaxy, in the halo of our galaxy. The 2 broad ones are formed in the Large Magellanic Cloud, which has a radial velocity shift relative to the galaxy. So you can see that the stellar sodium lines are shifted, redshifted, to the velocity that star has in the Large Magellanic Cloud, whereas the galactic interstellar lines are, of course, unaffected by what this star is doing 170,000 light years away. All sorts of neat things in spectra. And finally, I have one more star to show you, and very pleased with this one because we have made an important discovery, which makes it a second R127. It's its name up there from the Henry Draper Extension Catalog, 269582. It's an LBV. It was not really confirmed as an LBV before our work because there weren't enough data. You see big gaps there with no data. No one was interested in this star, but fortunately, some people had observed it. And you see a 12th magnitude, very faint. And that is the magnitude that R127 had. You know, I forgot to mention, I studied R127 when I was on Saratoga staff in the 1970s, and I discovered it as a very peculiar mission line object with similar to a very small number of stars, a very rare, and then I discussed that group of stars, and then in 1980, it became an LBV, and then that was the first that we knew that this particular class of peculiar mission line stars is really a quiescent state of LBVs. And again, I contributed to that. So this star was being observed here in the early 1990s, and it was 12th magnitude, and it had a spectrum like R127 had before. And then it did the same thing that R127 did, and now it hasn't gone as bright yet as R127, but maybe it will. R127 had a bunch of glitches before it got up to the top, and it has started going back up again. And so this is a light curve of this star from 1990 to 2016. And of course, we have the spectra. And this is maybe my favorite spectroscopic. This one is interesting. The previous one was boring, but you see here the first one, which is from 1994, taken by British astronomer, 2 British astronomers, one of whom is here, Linda Smith and Paul Crowther. And here you see not nitrogen 2 as you do here. Remember we saw that, and that's like 20,000 degrees. But nitrogen 3, it's a little bit blurred here, but this is doubly ionized nitrogen, these 2 strong ions, and had ionized, doubly ionized helium. Helium-2. So this means this star at this epoch was much hotter than it was here. And this is what I call an OFP/W9 star, and it is the discovery that this star had that state right back when it had the faint magnitude. 12th magnitude, remember? And now it got cooler. It got as cool as R127 was at the beginning of the sequence I showed you. And now look at this whole forest here of iron 2 lines, A-type spectrum. Very, very cool, 10,000 degrees. So it's gone from 30,000 degrees, 20,000, 10,000, and now it's started back again. Getting hotter. You can sort of, well, not quite. The nitrogen lines aren't showing up too well yet. It's on the way, or at least it's headed in that direction. So we have shown for the first time that this star is another bona fide LBV, which has now been observed all the way from its minimum state, 12th magnitude and a late O-type spectrum, to A-type spectrum near maximum. That's one of the neatest things in this paper, because that was not previously known. Here you see what we have of the light curve, and again you see the same effects that unfortunately there was almost no photometry here, but we showed that it was faint back before this in the 1990s. And now it's bright, and these are all iron 2 A-type lines. This is a forest of lines you saw before in the lower resolution. And now it's started to get hotter again, and these lines have weakened, and some higher ionization lines are appearing. Same thing, same story, same lines. Here you see the nitrogen 2 lines in this wavelength range very clearly there. Disappear completely, replaced by iron 2 lines, and then coming back toward, you see the helium, here you see in the helium how it was strong, disappeared. This is an iron line, and coming back now as it gets hotter again. Similarly over there. So that's what these stars do. Someday we'll understand why. And this is the final plot here, putting all of these stars and a couple of other ones, 2 of which are in the paper, and one of which isn't even in the paper, Estoratus, on the same diagram of brightness versus spectral type, OBAFG. The sun is a G star. The hottest stars are O stars, and BAF are intermediates. And so the point is this, is to show that you plot all these stars in this diagram, and they all do the same thing. There's this correlation between their brightness in these outbursts and their temperatures or spectral types. And that is a very important clue to what is happening, the physical mechanism that we don't understand, and this is what has to be explained. How and why did they do this? So actually one of my co-authors made this file. This is the last slide, and he kindly quoted some of my prose in this slide, which is really the sort of main point and conclusion of this whole study. Thank you.
Okay, so questions. Do we have any questions from the audience here? Yes, in the back there.
Your last chart shows that as they get cooler, they get brighter. Is that because they're getting larger?
Yes, they get brighter in visual magnitude, but not in the very first slide. Can you go back to the first one on this, or you just have to flip back? That's an astute point, and that's a crucial point. They get brighter in visual light because the ultraviolet energy is being reprocessed by this expanding, cooler envelope to lower temperatures. But what the chart I showed, the graph in the very first slide, shows is that they're bolometric luminosities, which is the sum of all wavelengths, all energy being emitted by the nuclear reactions, doesn't change. See, those excursion lines are flat.
Right.
Doesn't so, and again, that's a clue that this is not the energy generation that is changing. It's not the evolution. It's some structural instability inside the star, which is causing these expansions and whatever readjustments inside the star, and the energy generation just goes on the same as it was, but the visual magnitude, which is becomes enhanced at these cooler phases, and that's what I've been showing you in the light curves and in this final diagram. So that's a very important point. Thank you.
Right. Yeah, we actually had a little bit of that discussion online, just clarifying that as they get brighter, they're actually getting cooler, and it's due to the swelling, the expansion and contraction of the star.
Yeah, and then a reprocessing of the hotter radiation to lower temperatures, but the total amount of energy emitted by the star is not changing.
Right. One person wanted to know if it had anything to do with solar flares. I said I didn't think there was any real connection with flares.
Well, since we don't know what this is due to, it's
Okay.
hazardous to say no, but the sun is a cool star, and the physics of cool stars is very different. It's dominated by magnetic fields, and maybe these stars have some kind of flares or something. Certainly, some of these ejections are of circumstellar nebulae are not spherically symmetric. They have preferred axes and directions. So there's lots of peculiar physics, but most likely it's not out of the question. Magnetic fields are involved in some way too in some of that, but it's different physics from what you have in cool stars.
Okay. And the green shirt back there.
Do the stars pick up additional material either from a neighboring star or from interstellar space?
All right, so let me repeat that for the online audience. Can stars pick up material from neighboring stars?
Or interstellar space?
Very, very neighboring stars, namely binary companions, as we mentioned over here. When you have two stars that are very close together, some of these stars, you have two massive stars closer than the sun is to the Earth, to each other. And when they start to evolve and expand, the one that's expanding may dump huge amounts of material into the other star and actually invert the mass ratio, such that the original star, which is lower mass and therefore hadn't evolved yet, becomes the more massive star. And then it gets its lifetime extended maybe, and then goes through a different evolution than it would have if it had been by itself and just evolved as a star of its initial mass.
So would that change the temperature?
That's can be it's probably a pretty dramatic event. We see stars that appear to be exploding or whatever, but not supernovae. And some of those may be mass transfer events, sudden mass transfer events where a lot of material gets dumped into the star. But at least in some cases, then they can settle down, and then they carry on their new evolution and their new lifetime with different masses.
Okay, blue shirt, yeah.
There's variable stars have been studied for decades and decades. Has any of that study produced an understanding of the mechanism of the variation, and is that similar to, or does that have any application to what's happening in the blue variables?
Okay, so the question was, variable stars have been studied for decades. Does that indicate what the mechanism that's underneath this variability?
Well, of course, there are many different kinds of variable stars, as you probably know, and so and they have different causes. One of the neatest ones is eclipsing binaries. These two stars going around each other, if they're aligned just right, will eclipse each other, and then you can determine the period very accurately, and that's a whole industry studying eclipsing binary stars, category of variable stars. Some of the most famous variable stars are pulsating variable stars, and there's instability strips in the HR diagram, which are not shown here. This mostly affects lower mass stars at cooler temperatures than shown here. And when they try to evolve through these strips, they become unstable to pulsations. And so they start expanding and contracting periodically on timescales of days, from a few days to tens of days. And the most famous of those are the Cepheids, and they turn out to be extremely useful because they were discovered early on, and it was discovered that their period is related to their luminosity. And so you can measure the period very easily, and then the apparent luminosity, and then from that you can derive the absolute luminosity and how far away they are. And this is one of the main ways of determining distances to external galaxies, is through the pulsation, the periodic pulsations of Cepheids, and there are libraries and different instability strips that have these periodic pulsations. So that's fairly well understood, and that is not what's happening here, although it's not to say there's any relationship. Remember I showed you up at the top of R71 there, something like pulsations. So somewhere in the outer layers of the star, some kind of pulsation instability has been triggered by other things that are going on. But these are major readjustments inside the star, not in the nuclear reactions, but in mass motions inside the star, convection, moving material up and down, and those are the kinds of things people think of as models. And there are models and explanations of these things, but there's nothing yet which is so clear and definite that everyone accepts it as the last word.
Okay, we have a question down front.
Sort of similar. You know the orbital periods for these binaries, and could tidal forces play a role in causing this sort of massive redistribution?
So the question is, can tidal forces play a strong role in this massive redistribution?
They can, and yes, they can probably even trigger outbursts, especially in some peculiar kinds of stars. Sure, just like the moon affects the Earth's ocean to form the tides, the same thing happens in these close binary stars. Of course, the closer they are, the more massive they are, the more extreme the effects. And and you can study this. It's a fascinating, detailed field of dynamics and about how they rotate and they revolve, and then they get locked into synchronism, as the moon is, by the way. It always the same face, the same side faces the Earth, and they can affect each other. But most extreme effects that come to mind as you ask your question is very eccentric binaries, and for whatever reason, there's some binaries which are very eccentric. That is to say, they're almost linear. They have and the speed of the stars increases when they're close together, then decreases, and then increases, and they would buy each other. And at these periastron passages, when they're very close together, then there can be extreme effects, and some of these are binaries involving neutron stars or even black holes, which are extremely dense and have very strong gravitational fields. And you can get some kinds of explosions and outbursts and things which are triggered probably by tides at periastron passages in eccentric binaries.
Okay, I have one last question for you. Is Eta Carinae considered a luminous blue variable?
Yeah, that's a good question, and yes and no. You'll find it included in that diagram, up even higher. The thing about Eta Carinae is, because of our studies of it in great detail, it happens to be fairly close by, and the stars it's associated with, which are some of the most massive stars, 100, 200 solar masses, it's much more massive than these typical stars we're talking about. These tend to go, well, you can see here, the masses are there, like from 40, there's some surprisingly low ones here, but 40 to 80, say, is typical. Eta Carinae had an initial mass of 140 solar masses. And its outburst magnitude, when it had its huge eruption in the 19th century, was 6 or 8 magnitudes.
Yeah.
And that's much larger than these, as you were looking. If you're looking at my light curves, are typically 3 magnitudes. And so, is it the same phenomenon, more extreme, or is it a different phenomenon?
Yeah, that's exactly what I was wondering, because
we don't know.
Because it had such a huge outburst.
We don't know.
It
is an eccentric binary. And every 5.5 years, we've discovered now that it gets close and it has X-ray outbursts and things. Mm-hmm. And some people have argued that the binary has close approaches, and the great eruption occurred near one of them. So you can have something that looks similar, but it may have a completely different cause. Maybe this one is caused by these periastron passages of a close massive companion in an eccentric orbit. And these are not, although there are some people who would argue that all LBVs are binaries too. So that's where we are.
Right. And especially since these LBVs and Eta Car, et cetera, have these bursts that happen for years and decades, and you have to watch them over much more than a graduate student's lifetime, or even in some cases more than an astronomer's lifetime. It makes it quite a challenging problem.
It does, but that stimulates me to add something very fascinating here. We have an astronomer here, a German astronomer, his name is Armin Rest, and he specializes in light echoes. And these are delayed arrival of light outbursts from supernovae. He started, and then he got into Eta Carinae, by light scattered, reflected from dust clouds along the line of path. And it's all worked out. It's very complicated, but they can do it. And so he has gone into the Carinae nebula, and he has discovered and observed these knots which correspond to the historical brightenings of Eta Carinae. And he's found some blue ones, and I think we have the spectrum of the outburst. You know, there were no spectrographs in 1837 when this happened, and now, with this technique, we've been able to go back and get the spectrum of Eta Carinae and outbursts in 1837 before we had any spectrographs. Isn't that amazing? And the thing about Eta Carinae, one can let one's mind wander even further. It was reported by Ptolemy and I don't know who all as bright, much brighter than a normal star for centuries back before this outburst in 1837. Second magnitude, fourth magnitude, that's way too bright for a star, a normal star and its association. So it was already doing something centuries before this outburst. Now, the Europeans are building a 40-meter telescope in Chile. Is Armin Rest or somebody going to go back and get a spectra from 200 AD, 400 AD? Never say never in astronomy. You're likely to be wrong.
All right, this sounds like a good place to leave it. That we can, using the speed of light, look back in time, even at something that we know happened historically by looking at the echoes from it. So these variable stars will keep astronomers gainfully employed for quite some time. All right, next month will be our look at Cassini's grand finale at Saturn with Bonnie Meinke. Let's give Nolan one more hand of applause. Thank you for coming. We'll see you next month.
You're a great audience.
As far as I know, no. I haven't got anything definitive, but it doesn't look like it. Okay, here. You just go to, I wonder if it's listed on here.